A common misconception is that testing proves a program works. We imagine software as a pristine, perfectly engineered artifact. In reality, a successful test achieves the exact opposite. A good test is one that deliberately uncovers an error. Building a system is a constructive task. Testing it is the opposite. After months of careful creation, the engineer must reverse their perspective and systematically try to break the very thing they made. Adopting this hostile, adversarial mindset is the only reliable way to guarantee a product's structural integrity before it reaches the public. Hardware follows a steady wear-out curve, but software deteriorates. Every change spikes the failure rate. A threshold separates internal development from public release. Crossing it turns errors into defects, activating the defect amplification model, where 10 design errors cascade into 94 logic errors. Without a disciplined strategy to trap these multiplying bugs early, the customer becomes the de facto tester. And for any software company, relying on paying users to find your blind spots is a disastrous strategy. To stop that amplification, engineers test in the small before moving to the large. They start with unit testing, isolating the absolute smallest segments of code. This relies on white box testing. The tester pries open the component and looks directly at the internal gears and logic of the software. This flow graph visualizes basis path testing. Nodes represent decisions, and arrows map out every possible logical route. The strict rule is testers must design inputs forcing software down every single path. Every statement must execute at least once. Applying this microscopic rigor eliminates hidden traps in the fundamental logic long before any individual components are allowed to interact with each other. With internal logic verified, the perspective flips to black box testing. The code is completely ignored, focusing purely on what goes in and what comes out. Engineers use equivalence partitioning to group similar inputs together, preventing them from wasting time testing every variable when one representative number will do. This diagram shows boundary value analysis. Instead of testing safe, valid data points clustered in the center, testers deliberately push data to the absolute extreme edges. They want to see exactly what happens when a user pushes just over the line. Subjecting the system to these extreme inputs proves the software can survive the unpredictable and often illogical behavior of real-world human users. As those perfectly tested microcomponents are finally assembled, new friction points and interface errors are born. This triggers integration testing. Modern complex systems like web apps require entirely unique traps at this stage. You have to test navigation pathways, graphical user interfaces, and heavy server loads. Finally, validation and system testing place the entire assembled software package into a simulated real-world environment. Through this expanding spiral of traps, the software's actual output fails to match its expected output. A symptom is revealed, and the bug is finally trapped. Finding the bug is only half the battle. There is a critical distinction that ends the hunt. Testing is the act of finding the symptom. Debugging is the act of finding the cause. This is notoriously difficult because the external symptom a user sees on their screen is often geographically remote from the actual broken line of code. To isolate that root cause, engineers apply the scientific method using a tactic called binary partitioning. They systematically divide the system in half, continually eliminating the functioning sections until a single isolated fault remains. Isolating the root cause requires the forensic extraction of the antagonist from the system. It is a process of meticulous elimination, which brings us to the great irony of debugging. The very act of fixing a flaw alters the ecosystem. That new fix can easily introduce a brand new bug into an entirely different part of the code. This forces engineers to run regression testing, rerunning previous traps to ensure the new patch didn't break older code. But look how these pathways multiply. The reality is that testing every permutation is computationally impossible. You are never truly done testing. Eventually, time and budgets run out, the software ships, and the burden of finding that next bug shifts to the end user. Perfection in software is a myth, but the psychologically demanding, rigorous discipline of layered testing is what transforms fragile code into a robust, world-ready architecture.